What's up, hackers? Welcome to Attack on Tuesday. My name is Taggart, and tonight we are going to bear witness to what has happened to my binary exploitation skills, minimal though they were, in the last couple months where I haven't really had a chance to practice on them. I've been really busy with, building the lab and getting a course out for everybody, which was definitely not about binary exploitation, but it is something that I am interested in, something that I want to keep my skills up in. And so, much to my pleasant surprise, TryHackMe actually put together a really nice new introductory binary exploitation room called Pwn 101. And so I wanted to take a look at this room and see how these challenges go, and as a refresher, kind of go through how we do what we do with binary exploitation with the tool chain that this community has kind of come up with. And so we do things a little bit differently than what you'll probably find in other resources, right? Which is pretty much on brand, right? We don't use burp, we use zap. Same sort of thing. So generally speaking, the tool chain that you're going to find when you're talking about binary exploitation or disassembly, things like that, is you're going to find Ghidra, you're going to find GDB, the GNU debugger, right? And Radar, maybe, Radar 2. We don't use any of those, really. Ghidra sometimes, but we really have a different tool chain that we use here. And to kick it off, the first one that we use is Rizin, which you can pick up at rizin.re. And it's a really fantastic fork of Radar. And they have a nice FAQ about why they forked. And a lot of it was kind of community based. It kind of seemed like it wasn't a really good, healthy open source community, and we want to support healthy open source communities. So instead of Radar, we use Rizin as our command line based disassembler and debugger. That's kind of why we use Rizin. And then related to Rizin is a graphical interface called Cutter, which is just fantastic. It has a lot of capabilities, and I really like using it. You'll see what it can do today, so you can get that at cutter.re. So those are kind of our two primary tools that we'll be using for this. Then the other tool that we'll use, and this isn't particularly unique, is pwntools, right? The Python package. But the way that we use it might be a little bit different. At least for some of what we do. I find it's very handy, as you'll see, to, in our terminal, have a window open with, there we go, with interactive Python. So if I fire up IPython 3, you'll see that I have kind of a different kind of Python prompt here. And you can see that it's colored. Hey, Czar, so glad you're here. So glad you're here. If we do for I in range 10, right, you can see that I have like the ability to edit this stuff in a way that I don't in the basic Python interpreter, right? Print I. And it's just handy. And then I can bring it back up, and then I can move my arrow keys around, and I can do all sorts of stuff that, you would expect in a kind of a more modern interface. And then once I'm ready to go write my exploit, I can do that in VS Code, I can do that in Vim, whatever I want to do. But for kind of easy use of Python 1 bit at a time, I really like the interactive Python prompt. So those are kind of the three things that we're going to be using today. And let's get started. So Pwn 101, I already have it downloaded, and we'll start by taking a look at this thing. There are a lot of ways you can do this. Hey, Ginge. Missed the Memory Forensic stream, but watched the VOD. Oh, I'm glad you enjoyed it. Yeah. Saturdays always are interesting. So checksec is a tool that comes with pwntools, and so you can give that to, or you give Pwn 101 to it. And it tells us, okay, so we've got full railroad, no canary found. NX is enabled and PIE is enabled, but I don't think that's going to matter for what we're doing here. So the next step is we can either open this thing up. Obviously, let's look at it with file, right? It's a 64-bit executable. And so we can either open it up in Rizin or we can open it up in Cutter. I'm going to do both, just to show you the differences. So I'll start in Rizin. So I'm going to open it up in Rizin, and I'm going to open it up in debug mode, because obviously we want to debug this thing, and give it 101. All right, there it is. And then if you're not familiar with the Rizin command line interface, you just press question mark to get help for any of the things that you can do. And so right off the bat, there are analysis commands, and that is kind of what we want to do, because what we want is A for analyze all the functions and everything. So I basically give it 3 A's and just have it analyze everything, which gives us debug symbols and things like that. Okay, then I can use the inspect commands to get some more information. So I can use I to get binary information, and that would tell me there that it was a 64-bit, right? It would tell me that it's a little endian, and kind of any of the other stuff that I would need to know about it. I can use II to look at its imports, which is handy, right? If I see what kind of things it's importing, like functions. Oh, I noticed that it's importing system. Well, that's interesting. By the way, one of the cool things about the command line in Rizin that I think not as many folks know is that it does have some normal command line tricks. So if I wanted to just see the functions here, I could do II pipe grep func, and now I'm just looking at functions. So that's kind of handy. If you're used to doing things on the command line, and obviously I am, it's nice to have that kind of functionality. Other stuff I can do with the inspect, I have look at sections, and that will come in handy, especially when we do ROP. So when we look at the sections, it'll tell us the section start and end, and it'll tell us the permissions of the section. So for example, you can see we've got read write on data, we've got read and execute on these others, but not write. So really handy to have that data at my fingertips as well. And if I want to find the function that starts this thing off, I'll seek main. And then I will do PDF to print out the disassembly of the function. And that's literally what it is. So we're printing out the disassembly of the function. And so we're looking at the address here, the opcodes here, and then there are going to be some comments, like it's going to decode strings for us in comments. And I'm going to give it a little bit more terminal space here. Oh, perfect timing, Al. Welcome, Raiders. Good to see everybody. How did the stream go, Al? Whoa, Technique. Thank you so much for the resub. All right, so yeah, we're working in some binary exploitation today. We're doing the Pwn 101 room in Try Hack Me, and so I'm just kind of giving a tour of Rizin. So you can see that we've got these instructions coming in here. This is basically the entirety of the function, and I like reading it this way, but not everybody does. And so there is another option, which is Cutter. No, Kieran, take it back. Do not gift Helen a sub. She can get her own. Jay Haslow's, no, this is not Radar 2. This is Rizin, which is a fork. We do not use Radar. For reasons that are discussed in the Rizin FAQ. And I will also just say for everyone here, I know that it might seem a little bit finicky, but I would super appreciate it for anyone here if you did not refer to me as bro. I would just really, really appreciate it. It's not a term that I particularly identify with. I associate with a lot of really nasty experiences from my past. That's not the kind of guy I am. So, yeah, if you could refrain from using that term with me, I would just super appreciate it. I know it seems a little whatever, but that's me. So Radar 2 can be a pain. It's something to learn, right? Just like, and Rizin, which has a similar interface, is something to learn. Personally, I find it easier to use than GDB. But if you do not like the command line interface, guess what? We have Cutter. So we're going to run Cutter on 101 here, and I'm going to show... Oops. This Cutter. Ooh, I have to chmod it, I think. Chmod plus X. I just downloaded the new version of Cutter. There we go. That's better. So Cutter is going to give us sort of a graphical interface that wraps around a Rizin-like tool. So as you can see, we have a dashboard that gives us a lot of the information that we just saw. And we have the functions listed over here on the left. We have a strings breakdown. Imports, which we saw before. And the cool thing about imports is that it'll even tell you the unsafe ones. Whoa, Foot, happy anniversary. Good to see you, and thank you so much for a year of subscribing. That is crazy. So let's get some thank yous out of the way. Darth Webb, fun player. That guy Kimnick runs this from Master. Thank you so much for the follows. Alhezen, thank you so much for the follow. And let's see. Hate how they have you used the immunity debugger in the OSCP lab. Immunity is good for Windows though. And I'm using Pwn tools. Yes, you'll see Pwn tools going on GIFRAM as well. I have that I will have that loaded in this. This window right here is interactive Python. So if I do from Pwn, import everything, right? Now I'll have that. And just to show you what I can do with that, if I could do elf equals elf Pwn 101, right? That'll load that right up. And I have that now inside of my interactive Python window. So it's nice to have it here as well as in the debugger here. Linux Parrot, you can call me senpai, although I was a Kung Fu instructor, so the term would be shifu. Hey GIF, thank you so much for the subscription for 3 months. Very kind of you. All right. So one thing I will say about Windows debug is there's a tool that I need to get familiar with that kind of just came out called HyperDBG, and I'm excited about it. Yeah, you can use Pwn tools with Windows. It has PE capabilities, but there's also this new thing that just came out called HyperDBG, and I'm pretty excited about it and what it can do. Because rather than WinDBG or Immunity, which was kind of not necessary, well, Immunity a little bit more, but like WinDBG was designed as a debugger for developers, whereas HyperDBG was definitely designed a little bit more with security professionals in mind. And so it has a lot of really cool capabilities inside of it. And admittedly, I'm still learning about it, but I'm excited about its possibilities. And we'll do it on stream at some point once I'm feeling a little bit more confident in how it works. But we're not doing Windows BinX today, so we're going to stick down in here. So over to Cutter, just to show you what else we have. We have the symbols listed here. We have the Windows. I should see sections. But we also have a graph, although there's not much of a graph to be shown for this particular application, or this particular program. So if I wanted to look for the main function in disassembly, oh, there's the graph, right? If I wanted to look at it in disassembly, right, I've got my address space here, and I have the opcodes here and the decoded strings, things like that. But the other thing that you get in Cutter for free is the decompiler. And it is going to use the Ghidra decompiler, which is pretty nice. So if you're more comfortable reading this in a C-like syntax, it'll do a pretty good job of coming up with that for you. So you can see we've got void main, right? And we have a single kind of 2 variables here, a car pointer, and then a var, an unsigned 64-bit integer called var for each, and you can rename these however you want. For example, if I wanted to rename this, I could call it like magic number, and now that's just called that inside of my session. So I don't have to rely on the disassembler's names for things. I can make them my own. Okay, so let's look at the logic of this thing. And I actually, at this point, kind of prefer looking at this stuff in disassembly. So the first thing we have to think about is what's going on the stack here. And so remember that the stack is going to grow from high addresses to low addresses in memory. And the reason that matters is that when we make space for new stuff on the stack, we are subtracting. Okay, we're subtracting from our base of the stack, moving up. And that's exactly what we see going on here. That for our two variables, we have base pointer -4, and then base pointer minus 0x40. Don't forget we're in hexadecimal. That's not 40. That's 0x40. Another reason I love to have IPython up is I can just give that, right, 64. Last in, first out is usually how that's written. Or no. Yeah, it's last in, first out. That's what stacks are, right? Because it's like a stack of plates, right? So it's not first in, last out. It's last in, first out. So the opposite. So when we see this going on, what we know is that this one right here, this value is this much space. It's 4 bytes, and then this car pointer here is going to be 0x36, right? So, because that's how much back it is from our base pointer. Now, all of that being said, we don't know what they do yet, but just to get a sense of the size of the things, you can do it really easily. There's going to be some math later that you can see about how to do that, but this is kind of the easy way to learn how to do this. And hey, GIF, thank you for the resub. Appreciate that, friend. Now we're doing some like preamble stuff. These, by the way, notice are comments, right? This isn't actually assembly. These are comments that Cutter is helping us out with, right? They're not instructions, but here are the instructions. So you see here, we're pushing the base pointer onto the stack, the existing base pointer. Then we move the existing stack pointer to the base pointer, which now becomes the new base pointer, right? Because we kind of leapfrog those two pointers as we move through stack frames. And then we subtract 0x40, look familiar, from the stack pointer, meaning we're creating that much space in the new stack frame. That's what you should see this happen pretty much in every function preamble in x86 assembly, right? Where we leapfrog the base pointer and stack pointers, and we make space for whatever else we need to have in the stack. That is what's going on here. And then we're moving stuff into stuff. So in this syntax, we're seeing that we're moving. That is the it's not the unstacking process, Wally. It's the creation of a new stack frame. So every function has its own slice of the stack that it uses. And so what we're seeing right now is we're establishing the space for this function's stack frame. Now, the teardown of that happens at the end of the function with the ret, and then the return like tells the assembler, or tells the CPU, I should say, to like go back to the return address and knock off the base pointer and like go like disassemble that stack frame basically, or deconstruct that stack frame. So we're not there yet. We're establishing the stack. Now we got to use it. So here we're moving this magic number, which we just named, right? But keep in mind that this is something that catches people out when they first start reading assembly. They're like, oh, it's a variable. Nah, 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 nah. The brackets around this mean that you're really talking about a reference, right? So you're talking about data that is referenced at the address here. So whatever this address is, there's data there, and that's what we're getting. This is the assembly equivalent of a pointer, if you're familiar with pointers in C. Or other languages that use pointers. But so anyway, magic number is really better named. I should have renamed somewhere here, right? No, I only have that in the decompiler. Fine, whatever. Oh, no, there it is. Rename. We'll call it... special num pointer. Okay, so now we know that it's a pointer. And what are we moving to it? 0x539. What is 0x539? Well, it's a number, right? We can find out what it is in decimal. 0x539 is 1337. Ha 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 ha. Cute. We don't know what they're doing with it yet, but if we kind of look ahead, it's their cute little exit code. They're exiting with a code 1337 because they're leet. Whatever. So this actually doesn't matter for what we're doing yet. In fact, to that point, we can even rename this like exit code. Fair warning, we're probably not going to get through all 10 challenges in the room tonight because we're going to take our time and explain what's going on with the ones that we do get through. For my edification, honestly, to make sure that it's ingrained in here, but also for anyone else who really wants to get the basics down pat. In binary exploitation, I want to make sure that it's super clear. Okay, then we are moving 0 into the EAX register. Quiz for the chat. What does in the A range of registers, what does A stand for? What does that register do? And why is it the A? Hey, Neon. We are working on Pwn 101, and you are absolutely correct. The answer is accumulator. Its job is to collect stuff. So generally speaking, the A is going to be where output, input, things like that, results of functions, depending on what kind of function it is. But the accumulator register. And in old computers, like 60s computers, the A register may have been one of the only ones that you had. But that thing was where the result of the operation was going to get stored. A little bit of computing history there for you. So these things in orange, these are references to other functions, right? There's a setup function in here. There's a sim setup over here. There's a banner over here. And we can click on those and see what they do. But they're kind of not that important for what we're doing. You can certainly explore those, though. But the banner, of course, is kind of handy. The banner is, if we go into it, you'll see it's like, there's our Pwn 101 label. And what it's loading that string, which is stored in memory. See, there it is. It's weird looking, but there it is. And then we call puts to print it out. That's basically what the banner does. And now we're back in main. So we have this string. It says, hello, I'm going shopping. My mom told me to buy some ingredients, but I have low memory capacity, so I forgot. It prints that out, and then it says, type the required ingredients to make. It's misspelled. That's supposed to be biryani. But whatever. And then we print that out. Now, this is kind of what's interesting, right? This LEA, chat, what do you think LEA stands for? What does that opcode stand for? Load effective address. Absolutely, Kaizen. Good job, Neon. Now, Neon's gold starboard is all filled up. But yeah, load effective address. And remember that in x86 assembly, we do destination, comma, source. So we're loading into RAX, which is our 64-bit accumulator, the value represented at pointer S, which we had up here, basically. And then we're going to move that value from RAX into RDI, which is an argument slot for functions. Then we're going to move 0 into EAX, which is part of the same register, just the bottom 32 bits of it. And then we're going to call gets. So we're waiting to get a string. Now, here's the trick. The get string part of this is unsafe because there's no check on it. There's no guarantee on that the amount of data that you get is going to fit within the buffer that you're pointing it toward, which is S right here. And that's the core of buffer overflow. Let me try this. I'm not sure if this is... I'm going to have the man page for this. No, I don't on Kali, but I should have it on WSL. Yes, I do. Okay. So in my WSL, look, if you look for the man page on gets, the first thing it says is never use this function because it isn't safe for that reason, right? So just be aware whenever you see gets, especially in challenges like this, it's kind of a tell. It's like, oh, okay, that's where the vuln is. And if you ever find a developer who's using gets, you have to spray them with a spray bottle and say no until they stop. And then this is kind of the linchpin right here. This CMP, we're comparing the exit code to 539, right? You're searching for gets on GitHub. Oh, you're gonna find it plenty of times. I mean, I've shown grep.app on this channel a bunch of times, but like gets is gonna be around. Let's do case sensitive. You love to see it. Language C. There you go. So it's out there. Have fun. Here, I'll put that link in chat for everybody. Have fun with that. Yeah, grep.app is wild. It's I don't really do bug hunting, but it is a bug hunter's paradise if you wanted to go ask for some free CryptoCat. Some free CVEs. Oh, hey Matt. ReactOS might actually have to do that. Because ReactOS is like trying to re-implement the Windows API, right? So they may literally have to do that. Remind me after we finish this challenge. I found the funniest thing in the ReactOS documentation, and I would like to share it with you because I think you'll appreciate it. It's very funny. And by the way, ReactOS is actually a killer reference for the Windows API. But yeah, remind me when we finish this particular challenge to go and look at the ReactOS docs because it is quite good. Right, so it's the exit code, but it's also this thing that it's using. I actually am going to rename this to magic number because it does more than just do the exit code, right? Magic number. So we're comparing it to 0x539. Hey, developer. And if it's not equal to that, we're going to jump to thanks for, here's a small gift, and then we call system with bin sh. So it actually gives us a shell right away if the magic number does not equal 0x539, also known as 1337, right? So we have to break that in some way, shape, or form. So pretty simple right off the bat. We now know that this buffer is 0x40, right? It's 64. So if we do something like 65 A's, because I'm a traditionalist, right? In theory, we will be overflowing that buffer. Now we're going to run DC in Rizin because we loaded this thing to debug. Can we look at the decompilation? No. Learn how to read assembly. Yeah, of course. I'm just broken now. I hate C so much that I prefer to read the assembly than look at the fake C. But it's literally this. So going back over to Rizin, and this is why I like having both Cutter and Rizin working for me, okay? Because I can work both. All right, good night, Kieran. Thanks for hanging out. Lovecraft, I refuse to read anything not ATT assembly. That's a cry for help. Okay, so that's actually cool. So we got an error that killed us, and what I want to do with that actually is do a DR to look at the registers. No, nothing. All right, I'm just going to quit out of Rizin for a second, just run it straight. Yeah, well, the good news is, Kieran, that it's recorded. For those of you who don't know, we record this stuff and we keep it on YouTube. And, by the way, if you didn't know, I just put out a web app course through TCM Security, and because you're here, you get 50% off. Use code USERIZIN at checkout. And you'll get 50% off. And by the way, TCM is doing some crazy stuff right now. They are they're offering their PNPT prep course for free streaming. And so if you want to get in on the prep material for getting the PNPT certification through TCM Security, go check that out. Let me grab the enroll link for you right now. So basically, you have to show up for the streams, and it's like 2 streams a week for like 25 weeks. It's a big investment of time, but then at the end of it, you'll get lifetime access to the 5 courses that are part of the PNPT. Thanks, Neon. Thanks for that link. Yeah. Hey, Black Sheep Spicy. All right, so we're going to run this right here, and we're going to make some biryani. Okay, cool. So with our 65 bytes, we were able to overflow the buffer, and now we're in a shell. Now, I'm just doing that on my local system. That's not super helpful, right? Because what I want to do for real is do that here. On this IP, right? Port 9001. So I'm going to just use netcat to do that. So go to that address, give it 9001. And then I'm going to give it my 65 A's to overflow our 64 byte buffer. And then if I do an ls, you can see I'm in a shell now, right? So if I do cat flag.txt, kaboom! There's our first flag. So let's quickly recap that one so everyone's familiar with what happened. So the first thing we found was that in the variables that our function was using, we found a 64 byte buffer right here. And we knew it was 64 bytes based on this right here, and based on how much the stack pointer was subtracted to make space in the stack. So that's what we knew about it. Now we could have also done some other kind of cool experimentation to find the size if we didn't know it that way, but that is the way I prefer to do it because it's just a little bit more exact. So what happened was we overflowed that 64 bytes with an extra byte. And what's right next to that buffer in the stack? Well, it was this variable called magic number, which was 4 bytes, right? And don't forget that even though the stack grows from high addresses to low addresses in memory, right? So it feels like it grows backwards. So that's why when we see a subtraction from the base of the stack, it's making more stack space, right? That's what's going on. Even though that's true, so that's how space is made in the stack. But so space is made in the stack by subtracting, but space is filled from this subtracted down back toward those higher addresses. So the reason that matters is the first thing we had right in our stack was a little bit of space for the magic number. Then we had a bunch of space at the buffer. We filled that buffer with 64 bytes of space, and then we filled it with one more byte of space, taking over that magic number. And because that magic number got messed with, this check to see if the magic number still equaled 0x539, also known as 1337, because we messed with it, this conditional failed, and we got jumped over to the shell. Any questions on that one? I know I'm doing like a lot of gesticulation. I don't have good visuals for this. I've never found a good visual that I really like for the stack. I should probably make one at some point. All right, we'll close out Cutter for now. We'll go get the next challenge. All right, this is called pwn102.pwn102. Handy. All right, let's chmod it. I'm probably going to make some for my upcoming BinX guide. Yeah, well, you should, Sar. I'm waiting for that thing. I have so much hype in the hype tank for your instructional materials. I am ready to advertise it on all platforms. All right, what does this thing do? I need bad food to feel dead. Oh, brother. Am I right? I mean, let's give it the same 65 A's, see what happens. I'm feeling dead because you said I need bad food. Uh-huh. Yeah, dead beef. Like, you can kind of tell what's going on already because these are both words that you can make with hex values, right? So let's get right into it. So we're going to fire that up in Cutter. And I'm going to load it up in Rizin. And this, by the way, is why I find it particularly funny. Like, when, I don't know, I know that there are some folks on here that use this, but, like, I don't know why everyone decided that 0x was, like, the hacker prefix for our names. I don't know. I mean, you do you. That stuff just bounces off of me, though. That's why I pretty much just go by my name. I'm me. What you see is what you get. I was like, I'll never forget the first security conference I ever went to. Somebody came up to me with, somebody came up to me with like just the confidence I'll never have. It was like, hey, how you doing? I'm Lord Nightmare. I was like, okay. I will never know what it's like to live that life. Hey, Digital Warhead. Kaizen, usually we run for like 2.5 hours. I was like, what kind of estimation of your skills do you need to have to use that as your name? Whatever. You start to move away. The Lord Nightmare Discord. Like a less hot Hannah Montana sometimes. A less hot Hannah Montana, I mean, you're not starting from the... Okay, so what do we have here? Whoa, GoPro! Lurking and then shows up with the resub. Good to see you, bud. Alright, so what do we have here? Once again, take a look at these comments. We have 3 variables. We have this massive... This large boy right here, which is likely going to be a buffer of some sort. We have a couple of, looks like 32 or 64-bit integers, right? Agent OP, thank you so much for the sub. And then the same kind of stuff that we saw before. I'm going to try to do this one more in Rizin so you can see what the differences are. And then, okay, so take a look at this. We have 2 variables, one of them at 4 back and one of them at 8 back. So the one at 4 back is 0x bad food. And the one 8 back is feel dead. So that's interesting, right? We'll take a look at that to see what those are all about. And then... as we go through, we've got the string loaded up. By the way, just in terms of like getting used to reading assembly, whenever you see a D, especially a DI, right? Whenever you see that, get used to thinking those are function arguments. Those are things that functions are going to use, because that's in our calling convention. The DI register is the first register. It's the first argument to functions. That's where those are stored. And so this string is getting loaded up into that register, and then printf makes use of it, right? So printf, that function's going to go look in this register for like, what am I supposed to print? This is what you're supposed to print. Wonder Wookie 89, thank you so much for the sub. So printf gets called, and then we load the pointer at the value stored at the 70. And then we've got RSI, which is, by the way, argument number 2. DI, which is this %S. So we're looking at a format string. This ISOC99 scanf. This is a totally weird thing, and you'll see it all the time. We're looking to read input that is a number. Okay? So it's like gets, but it's going to translate whatever you put into it as a number. Now, this is the part that gets a little bit more interesting. Remember last time we saw that compare, that CMP, and we compared the magic number to 1337. And then if it wasn't that, we got our shell. The same sort of process is present here. Notice that we have somewhere here, we've got a load bin sh into that RDI register, which I told you was our first function argument, and then call system. Okay, well, how do we get there? Well, we have these 2 compares up here. One of them is comparing that 4 back value to the number 0x coffee. And the one at 8 back is compared to 0x code. Okay. So plainly, we have to mess with stuff. Because remember, those same variables were set here to bad food and feel dead. So our objective is to change those values through whatever we send in through input to coffee and code, respectively. Which means we have to be a little bit strategic about how we do this. The first thing is we know how big our buffer is, right? We've got 0x70. How much is that? 0x70. So it's 112. Okay. That's how far back it is from the base pointer, but that's not how big the buffer is. How big is the buffer actually? This track rips. Okay, so it is not actually 112 bytes. The reason why is because of these values here. Keep in mind, it's like the staff for I'm totally blanking on the staff of Ra in Raiders of the Lost Ark, right? You have to take back one Kadam. Because even though we're subtracting 112 bytes from the base pointer, there's other stuff in there between us and the base pointer, right? There's, in fact, how much? For 8. So there's, in fact, 8 bytes already accounted for that isn't buffer related. And so, in fact, we have 104 bytes of buffer. Right, 112 minus 8 is 104. That's how large our buffer is. Okay. So we'll actually define that in IPython here. We'll say overflow len equals 104. And so we can say something like payload equals, we'll give it a bunch of A's times 104. And notice that I'm using a little b in front of the A's. That's because I'm making a byte string. Got to do that, because what we're going to be sending is raw bytes. Okay, so that's our overflow length. And then after that, I need to mess with these. So the next thing after I overflow that is going to be the 4 bytes that have to do with feel dead, right? So if I have that right, I'm gonna payload plus equals, I'm gonna make those B's for testing. And those are gonna look like 42s when we look at it in the hex dump. Oh no, 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 no. There. Payload plus equals, not payload equals. There we go, we're adding to it. And just B, 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 B. And then we're gonna add C, 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 for hey Wonder Wookie, you can just do bang Discord. Right. Hey, Digital Warhead. Listen, I'm just a big old dork, and I love this stuff. I think that's part of it. It's just like, I love it. I've been obsessed with computers ever since I was a kid. My dad had kind of a weird job. He did voiceovers for flight simulators in the 80s. And actually, he did it for de Havilland, if anyone knows the Canadian company, the de Havilland. They make the Dash 8. And they also made the Mosquito in World War II. Anyway, so de Havilland, they made flight simulators, and like they were experimenting when I was growing up with touchscreen interfaces, right? So my dad was doing all the stuff with like new kinds of technology. So the bottom line was there were all kinds of computer parts in different states of disarray all around my house at any given point. And if I wanted to make anything work to like play a game, I had to put it together myself because my dad wasn't interested in helping me. And so that's kind of how that started. And even though my formal degrees are in not computer science, I've just always been super fascinated by this stuff, in part because anybody can learn it. And the information is out there for you to find, which is really, I think, one of the most beautiful things about this realm. But it really is. It's nothing special. It is just practice. It is. It's just putting in the work. Okay, so we have this payload here, and are you actually, just like if your degree is in computer science? We are a bit of a pack of strays, aren't we? Certainly. And as an English major, I resemble that remark. And as a former educator. Strike that. I'm still an educator. Japanese literature. GoPro. Fun fact, I entered college as an East Asian Studies major. That didn't take, but yeah. What my formal degree is. My bachelor's degree is in English creative writing, and my master's degree is in education leadership. So basically the plan was like to run a school. Sun Tzu. I'm not a huge Sun Tzu person, although you will find me quoting Lao Tzu and Chuang Tzu. Like how Chuang Tzu said it was better to be the gnarled tree, for it is the gnarled tree that no one wishes to cut down. A whole lot of Taoist philosophy is just like, don't make trouble. This is how you avoid trouble. Okay, so we're gonna do this. This is kind of cool. What we're gonna do is we're gonna write this payload to a file and then use it. So with open, we'll call it payload.txt. And we have to open it in write bytes mode with WB. And try not to have the Animaniacs song get stuck in your head as we do that. As F, we're going to do f.write payload. Payload. And then coming back over here, we're going to quit out of Rizin and then reopen it. But we're going to reopen it with some different arguments. So we're going to do Rizin, but then Rizin has this really cool thing it can do, where you can give it what's called a RZ script. And you can write whole files that have these, right? But you can also send them in with a command line. And the option that we're setting here is that the standard in is going to be pulled from payload.txt. That allows us to send raw bytes into the debugger without having to try to like copy pasta them, which you can't do. GoPro has redeemed Play Me a Song, which I will do once I load this up. And we'll do debug 102. Wonder Wookie, you're completely new to binary exploitation, aren't we all? And I'm sorry if you have been asked this, where would you start? Any good video courses for assembly? Wow. Frankly, I'm like, wait for SAR to finish his stuff. Is probably going to be the best thing that's out there. No, it's tricky. Binary exploitation is this thing that like everybody likes talking about and everyone likes doing, but there is not a whole lot of great intro material except I'm gonna get vivisected by SAR if I don't mention pwn.college. And that's probably the best place to start, is pwn.college. Both the lectures on the material and the challenges that they have for you. I think that is absolutely the right place to get started. Now, it's a time investment. It is. But it's well worth it because you're essentially signing up for a computer science degree, like the missing semesters of a computer science degree even. It is really, really solid, really detailed stuff. All right. It does expect a bit of prerequisite knowledge, for sure. All right, let's get this song thing going. Okay. Song.
Testing. How we sounded? I think. Okay. GoPro, your call. Do we do... I'll give you a choice of two very disparate artists. Bo Burnham, we'll do a Bo Burnham, or Billy Joel. Billy Joel, didn't expect that. All right. This is one of my favorite Billy Joel songs. This is called Miami 2017. Seen the lights go out on Broadway. I saw the Empire State lay low. And life went on beyond the Palisades. They all bought Cadillacs and left there long ago. They held a concert out in Brooklyn to watch the island bridges blow. They turned our power down and drove us underground, but we went right on with the show. I've seen the lights go out on Broadway. I saw the ruins at my feet. You know, we almost didn't notice it. We seen it all the time on 42nd Street. They burned the churches up in Harlem, like in that Spanish Civil War. flames were everywhere, but no one really cared. It always burned up there before. I've seen the lights go out on Broadway. I watched the mighty skyline fall. The boats were waiting at the battery. The union went on strike. They never sailed at all. They sent a carrier out from Norfolk and picked the Yankees up for free. They said that Queens could stay and blew the Bronx away and sank Manhattan out at sea. You know those lights were bright on Broadway, but that was so many years ago, before we all lived here in Florida, before the mafia took over Mexico. There are not many who remember. They say a handful still survive to tell the world about the way the lights went out and keep the memory alive.
Okay.
Amazing event. We did meet, and
What
the
is this?
stars
Get out of here. There we go. All right. Thanks, everybody. Scenes from an Italian Restaurant. So I actually can do that song, but it's a million minutes long. Mastering that solo was like one of the hardest things I've ever done on the piano. All right. Back to work. By the way, nobody reminded me. Dan GoPro, thank you so much for the gift subs, and an anonymous gifter gifted a sub. Thank you very much to that kind stranger. Nobody reminded me to show you this funny thing from React OS. Let's see if I can find it. Yes, I believe. I don't want create remote thread. I want create thread, don't I? I think this is what I wanted. Yes. So I don't know if M Alpha is still here, but this is the funniest thing I found in create. And I don't know if this is true in the actual Win API, but create thread. Oh, awesome. So check this out. Their create thread implementation is literally just create remote thread with NT current process. I don't know if that's how it actually works, but I thought that was kind of funny. That create thread is actually using what you would think is the more complicated function, which is create remote thread. Act as if we're going to create a remote thread in ourselves. But why? Right, so let's see, where were we? Oh, right, we were about to run this thing. Where we have loaded up our payload into the debugger, and we're going to run it. But before we do that, we've run our analysis. Let's go to the main, not admin, seek main, and we'll go to PDF. We'll print that out, and the reason we're going to do that is we're going to add a breakpoint. We want this thing to stop execution at a certain point. Where? Well, we want it to stop right after we give it the data and before it does the comparison, right? Because we don't want it to do this jump. We want to see what our stack looks like. So we're going to write db, and d is the debug options, right? So db allows me to put a breakpoint command. So if I do db and then the address, you can see now that at that address, there's this little b here, and that is exactly how it identifies there is a breakpoint. So now we're going to run dc. And I don't have to type any input because I've loaded that payload.txt as my input file. Okay, so we got the banner, we got the message, I need bad food to feel dead, am I right? And then it said hit breakpoint at our breakpoint address. At this breakpoint, we're going to do a couple things. First is we need to look at the registers. The registers have a bunch of information that we need. And in particular, we need the stack pointer register and the base pointer register. Notice that these are totally different addresses from our cursor where the code was. But that's okay. That's what we would expect, right? That the stack is in these really high memory addresses because that's where the stack is supposed to live. But the stack and the base pointer, if you look at them carefully, the stack pointer is at C50, and the base pointer is at CC0, right? So the base pointer is at a higher memory address than the stack pointer, right? Because remember, again, the stack grows toward lower addresses. So the stack pointer is at the quote-unquote bottom of the stack, and the base pointer is at the quote-unquote top, right? But we're going to use this tool called px, which prints out hex dumps, and we're going to give it that stack pointer. And let's take a look at what we see in the code. We see this is the stack. This is where we saved our data. And sure enough, you see a bunch of A's and then some B's and some C's. So the way to look at this dump, if you're not familiar with reading these hex dumps, and it took me, by the way, forever to get even remotely comfortable with looking at this stuff. But what you're looking at is in the left column here are the memory addresses that start the row. Okay, so this 9C50, this is the 0. This column right here, and then 1, 2, and it goes on for 16 bytes, right? And then the next line, right? See, it increments by 16 or by 10 in hex. So that's kind of how that's going. You can see that going through. So let's think about what we needed to compromise. We needed to compromise 4 back and 8 back. So 4 back from the base pointer. Let's do a little bit of math here. We have our base pointer. Let's do 4 back from it. How do we do that? I like doing this in Python. So 4 back would just be -4. Okay, so that tells me that it's 09 CBC. Let's go find that. 09 CB0. And then look at the C column. oh snap, there's our C's. So we actually lined that up. Okay, we were able to line up those 4 bytes correctly. And then, obviously, if we do -8, CB8, let's take that column, and that's the start of our Bs. Right, 42 is the hex representation of Bs. So we actually got that right on the first go, which is unique. So we kind of know that we know we have our buffer length correct, and then what do we put after it, right? Well, remember that we have to do the 8 back has to be what? The 8 back has to be code. And by the way, notice that it's a different size, right? It's this right here. And then, because how many bytes is that? That's 2 bytes, right? And then 8 back is, or sorry, 4 back is coffee. So that's a little bit tricky, right? We have to take into account the differing sizes here. And we also have to think about how these values get encoded when we put them into this process. And this is where, if you've ever heard the term endianness, that's where this comes in. Where in little endian architecture, we store the least significant byte first, which essentially means that we invert the value. Let's see that in action. Pwn Tools has a really nice tool called P64, or it's an implementation of PAC, but P32 for 32 byte and P64 for 64 byte. I'm actually going to use P32 here for reasons that'll become clear. Watch what happens when I 32 byte PAC 0xC0D3. Okay, so I get a byte string back, but look what happened to the values. First of all, it padded it for me with 2 null bytes, these 0 zeros, which is very helpful. That's exactly what I needed. Because notice that I had these other values here. And so, if I pack C0 FF33, I have the same thing happen, but this one looks a little bit different. And I'm wondering if somebody who isn't SAR can tell me why I see this just rando 3 here, and then the /x FF /x C0 /x. What happened there? Alignment. This one is an alignment, but it's a good guess. Yeah, Alpha has it. ASCII 3 is 0x33 in hex. Correct. And so the reason that, right, it's printable. The reason I bring it up is because one of the hardest things about doing this work is kind of code switching, for lack of a better term, between bytes and not bytes, hex and not hex. There's a lot that you have to kind of keep straight in your head as you're working through all of this. And I think that's one of the toughest mental disciplines of binary exploitation. And so, you know, when you go through stuff like this, it's like, wait, why is it doing that? That's why. So yeah, that 33 there is going to be printable. And just to prove the point, right, if we do CHR 33, oh, wait, my bad. See, I did it again. I went to decimal when I actually meant hexadecimal. CHR 0x33 is the value 3. Just to show you that that relationship. Okay, so we have these two values, super handy, right? And each one of them, by the way, if we measure the length of these, is 4 bytes, which is real handy for what we're trying to do, right? Where we're trying to get these things within 4 bytes of each other, basically, right? Because 8 back needs to be code, and 4 back has to be coffee. And so our payload now, let's see, by the way, one of the cool things about IPython is I can just kind of type part of my command and use the up arrow to go back to where I was doing that. So payload, we'll start with the 104 A's. That's fine. And then we're ready to start messing with those values. So payload plus equals P32 0x 8 back is going to be code, right? Plus P32 0x C0 FF33 with, we'll rewrite that. Come back over here. And let's run that again. Now, I'm also going to do this another way. We're going to do this using Pwn tools, right? Like running the process through Pwn tools to show you how that part works as well. Let's try this though. Okay, and I'm going to analyze it. If you like IPython, you should check out bpython. I'm unfamiliar with bpython. What is that? bpython. Python, please. Ooh. 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 That is cool. Read line, rewind, save the code you've entered to a file, auto indentation. But can it do the cool stuff that IPython can do? Like this. If it can do that, I'm sold. If not, I'm going to stick with IPython. That is so fun for me, where you can run shell commands directly from IPython and save it to Python variables. Try Conch. So I have used Conch. I've spoken to the developer of Conch a little bit. I like it, but it's a little much for a day-to-day shell. I'll stick with my fish shell and then go into interactive Python when I need it. I tried. I had like a whole 2 weeks where I was like, okay, I'm all in. Let's try Conch as my daily driver shell, and I couldn't make it work. Okay, so we're going to put a breakpoint back in here just to be safe. And then we'll run continue. And, okay, we hit the breakpoint. Let's just see how our registers look as a safety check, right? So we're going to get that stack pointer. We're going to do the hex dump of it with px. Okay, and then this is looking pretty good. There's an 8. And then there's our code. And notice the null bytes, right? But we want those, because the thing is supposed to take 4 bytes. Okay, and then there's coffee. Looking pretty good to me. And notice how they're represented, right? We've got these zeros here because it was only a 2-byte value. So we're padding it with null bytes. And then here we have a single null byte that's padding it, and then coffee. Michael, thank you so much for the sub. All right, let's run this thing, see what happens. Created process 56755. So that actually worked out for us. To do it another way, if we cat payload.txt and we pipe it to 102, says, yes, I need coffee to code, but we don't get the interactivity. Which I believe may be an alignment thing. I think we might need to pad it with a stack, with like a ret to align the stack, because we're not at 16 bytes yet, or 16 bytes yet. Took your PWST course. I learned a lot. Thank you. Oh, you're welcome. And to make that a little bit clearer, if we look at our len of our payload, right? Yeah, divided by 16, or mod of 16. Oh no, it is divisible by 16. It's weird. Doesn't it just spawn a shell? It's supposed to spawn a shell, but it's not. Let's try it in pwntools, which is the other way I wanted to show it to you. So here we're going to do elf equals, we'll change that to 102. P equals elf dot process. Oh, you're right. If I'm doing it from the command line, I might need the cat trick. But let's try this. Elf dot process, because it is spawning a system shell straight away. Okay, so we've started the process. If we receive from the process, it's like a pipe. So if we do, or like a socket. So if we receive some bytes, we're gonna do p dot send, and we're going to send the payload plus a new line to tell it that we want it to go. And then p dot receive, p dot interactive. Okay, so the shell works that way just fine. Let's check. So we'll exit that and kill the interactive. And let's make sure we still have time on the machine. Let's add some. We're taking our sweet time with these, but that's okay. Now, I'll show you how to do this in pwntools rather than with netcat, because it might be a little bit cleaner. So we're going to do con equals connect, and then that IP address and port 9002. I think it worked too. Okay. So we're going to do con.receive. Let's get those bytes out there. Okay. Con.send. Payload plus the new line. Okay. Con.interactive. Yes! Cat flag.txt. Success! Okay. Exit the shell. Nice. That's 2. All right. Let's see what's up with challenge 3. I apologize for being a little glowing. It's stupid warm in this room when I'm recording. It's actually warm all the time. Thank you very much, Western exposure. But no airflow when I'm recording, so just be glad you're not in the same room. That's good news for you. Okay, so let's see what's up with this 103. Ooh, we have emoji. Husky would be happy. A THM Discord server. Cute. So let's see. I don't want to go through this whole thing manually. Ugh, boo. So I'm not gonna. Instead, we're gonna look at it in Cutter. All right, what do we have? We have some functions. We've got main. We've got admins only. Interesting. Announcements, banner, bot command, deregister, discussion, general, which are the commands I think we saw, right? Yeah. Bot commands, room discussion, general, announcements, rules. Okay. And then this admin only, which we haven't seen before. Oh, hey, Michael. You said you took the PWST course. You learned a lot. I'm so glad. Thank you so much for saying so. And for anyone else who's interested in an intro web app pen testing course, guess what? You can get 50% off just by hanging out. Use code USERIZIN at checkout, and you can go ahead and get PWST for 50% off. So that's like $15. Okay, so this admins only. Looks like admins only is going to call system for us. Very handy. But how do we get here? So one of the cool things in Cutter that I really like is this show xrefs. So we can see the cross references to a function so we can see where it's getting called from. It ain't. So since it's not getting called from anywhere, I think we're in ROP territory a little bit, meaning that we need the address of this thing, assuming that we don't have defenses against said attack. Railroad partial. Yeah, the PIE, that's... Sorry, I always confuse Railroad and PIE. Yeah, PIE is what we're looking for, and... Where... I guess PIC is what position-independent code, as opposed to position-independent execution. Yeah, checksec makes it a little bit clearer. Yep. So we're good. Yeah. Someone should write a guide on all these mitigations. Someone should publish a guide on all these mitigations. What is ROP? Ginge knows. He's a plant. He's my plant asking good leading questions for teachable moments. Yes, return-oriented programming. So we get to use my favorite metaphor, which is if we think about this whole thing, this whole address space, right, from start to finish, which, by the way, you actually have this. How cool is this? As like a videotape, right? What return-oriented programming is doing is essentially we're going to be able to make the program move to positions of our choosing by controlling the return pointer, and it would be like kind of editing a movie to make the actors say whatever you wanted them to say by modifying the time codes for the movie in different sequences. That's what RAW basically is. And essentially what we're doing is, if you think about, okay, this is where we actually do need a stack diagram, and I'm going to try to find one that I like better. Okay, I'll live with it. Yeah. So remember, okay, so this is the high address, going back to the low address. So this is old stack, new stack. But here's the part that I think, right, so as when we're talking about overflows, right, here's some variables, X, Y, and Z. These are variables, right? And you see how we have the base pointer -8, -16, -24, just like we saw in variables before, right? Moving back from the base pointer. Okay, well, look at what's right after the base pointer, this return address. Okay, the return address is super important, right? Because once the code is done, that return address is where everything gets pointed to say, okay, go back here. So if we're able to overflow into the return address and control that, now we can point the program to different locations in the code. And if we don't have any defenses against this address space being different from run to run, it pretty much looks like this every time, then we can easily determine the address that we want to point it to. And in fact, we have some tools already to make this happen. But before we do that, we got to find the vulnerability, right? We got to find the right spot for the vulnerability. So let's see. If we look at announcements, what does that look like? Puts. Just a straight output. We're not getting any input. What about... where is it? Bot commands, right? Bot commands. Puts. Ooh, there's a read. Let's look at discussion. Straight puts. And then general. Okay. Hope you're doing well. You found the vuln, right? I think we're in general is where the vuln is. And then there's this scan 99, which we've already demonstrated is vulnerable to overflows, right? We've already demonstrated that. So I think this is where we're at. So let's take a look at this function. We have, looks like a buffer of 32 bytes. Now for this one, we're going to do a couple of interesting things. We're going to load this up in Rizin, and we're going to try to break this buffer, but we're going to confirm the size. I'm going to show you how we can do this with a De Bruin series, also known as cyclic. So we're going to do Rizin D pwn 103. Okay. And we're just going to run this straight. Okay. Choose the channel. We said we thought it was in general, right? 3. Okay. Now, in Pwn Tools, we have a tool called Cyclic. And I know that there's one in Metasploit, and I know that there are other ways to do it. I like doing it this way. So I'm going to do Cyclic for 50, Alex. And we're just going to do a little copy pasta here. And put that right in here, and we'll see what happens. Okay. We got try harder. Gross. But whatever. and we crashed. But that's actually good news. We would expect it to crash if we broke this, right? If we broke the return address, we would expect it to, ugh. 3, 2, 1. We would expect it to crash if we overflowed the return address because the function would not be going to any place reasonable. Now, here's the kicker. In 32-bit applications, your error here is actually going to just show you the bytes that you overflowed into the return. Okay. But in 64-bit, the execution's a little bit different. There's a check to say, is the return address a reasonable part of my address space? And if it isn't, it just dies with a 0 on the instruction pointer rather than your overflowed nonsense. However, we can still find out where the overflow happened. And that's what this cyclic is all about, by the way. So this cyclic is this thing called a De Bruijn series. And basically, it's made of substrings that only occur once. And so by finding out which part we see in the overflow, when we feed it back into the cyclic find function, which is the complement to this, it tells us where the position was of the overflow. But the trick is that in this particular case, we're going to have to add 8 bytes to that value, because we actually want to get 8 bytes more, right? Because we want to get over the base pointer, not just to hit the base pointer. So anyway, to see where that happened, we're going to inspect the registers, because as we said, the base pointer got before the return address. So if we look at the base pointer, something really ugly happened to it, right? That don't look right. It doesn't even have the same number of bytes assigned to it as we see with the other registers. And, you know, you get used to looking at these. These are printable bytes, right? 61, 61, 6A, right? These are the things that we gave it. And so we're going to take the last 4 bytes. 1, 2, 3, 4. Just take those. And we're going to come back over here. I'm going to run cyclic find. And 0x that. And it's going to tell us that the overflow is at 32. And that's decimal, by the way. Which we would, so remember that's hex 20, which is exactly what we would expect. That the overflow, right, that the buffer was 20 bytes long. But our overflow length in return-oriented programming, we want to get over that. We want to fill this up, and we actually want to start hitting the return address. So we add another 8 to that. Okay? So in our case here, the overflow length isn't 32, it's 40. Okay? And so now, if we fill up that buffer, fill all of this up to over the base pointer into the return address, now we get to write into the return address whatever we want. And what we want to write is the address for this admins only function that we're not supposed to get to, but we can if we control the return address. There are a couple of different ways to load this up. Obviously, I can just right-click and copy address. That's easy if I have it in Cutter. I can definitely just do that. That works fine. But I also have the ability inside of pwning to load this thing up. So if I change up my elf here to 103, one of the things that the elf object has is something called symbols. If I do elf.symbols, it's going to tell me all the symbols, including the local functions that it has inside of it, including its addresses. And if I look through them, you'll see that there's one called admins only, although I can't see it right now. I just saw it, right? You saw it too. There it is. So if I do elf.symbols admins only, and let's hex encode that. 401554, 401554. So we can get the address a couple of different ways, whichever one's easier for you. Or if you're scripting it out, you can use Pwn tools to just make that easy for you. Okay. So I'm going to take that. I'm going to assign that to a variable called admins only. Okay. And then we'll say payload equals a bunch of A's times the overflow len, right? Because again, what does admins only do? It's going to say welcome admin, but again, it's going to do that handy dandy thing for us where it's calling system for us. We don't have to work any harder. We just have to hit this function. It looks like we're good. Okay. Times overflow len. Oh, you're absolutely right. So what Sar is referring to is the fact that we don't actually want the admins only hex like that. What we want is we want a packet. Just like we did with our code and coffee values from the last challenge. We want to do P64 like that. If we do admins only now, it looks wacky, but it is correctly packed for loading in here as an address. So payload plus equals admins only. Okay, and payload. Yeah, okay. I think we're good. I think we're good. Okay. So same deal. We're going to take that. We're going to with open. Write that. And then we're going to... Yep. 32 filler plus... Yep. It's actually, sorry, in our case, it's 40 filler plus 8 rip. But yeah. And right, Rizin.d, or actually R, and we'll load up 3. Okay. Seek to main, pf. I was going to put a breakpoint somewhere. Now I can't remember where I wanted to put it. Let's just... Oh, this is wrong. I'm just realizing. This isn't going to work. Maybe at the end of the function so we can see the value being popped into rep by return. Yeah, you're right, but this payload is wrong. And I'll tell you why. The payload needs something else before the bytes and filler. The payload needs... that 3 new line. All right, let's see what happens. That actually kind of looks like it worked. But we're going to run that again. And this time, we are going to set the breakpoint at the end of the function so we see the value being popped into by return. Yeah. So, a seek main. Actually, seek general. Right. So we're going to print this out. And we're going to put a breakpoint right there. Or actually, right here. And we're also going to sim.admins only. We're going to put a breakpoint right here when we hit it. All right, let's run. Okay, so we hit a breakpoint at 401331, right, which is a compare. Now let's take a look at the registers. Nothing crazy happening right now, and notice that the instruction pointer is at our breakpoint, right? Because this is what's keeping track of where we are. This is our playhead, basically. Okay. Now, debug has a couple of other options, right? We can, instead of continue, we can step. Okay, now we're at 401080. Right, we're inside of string compare. Now let's now we're at 1020. Okay, now some weird stuff has happened. We went to the stack and then we came back, but notice that eventually we hit try harder and now we got to admins only. So we made that happen. Notice that the base pointer is totally borked now. It's filled with our A's, but our return address was set correctly, which is why we got here. Now, if we continue, it says create a process. So it worked, but we don't have it interactive. So we're going to go back over to Pwn Tools and do the same thing that we did before. So p equals elf.process, right? And then p.receive to get some data. And then we're going to p.send payload, which, by the way, has the 3 inside of it, so we don't even have to do that part. Okay? I broke it. Dang it. Oh, no. I'm good. Still had it. So we were able to pop a shell with that one as well. That looks pretty good. So let's try to run that one. Ah. Got EOF while reading in interactive. They did give us a warning. So you're working with an Ubuntu 18.04 LTS, so there will be a stack alignment issues. Make sure to add a ret gadget to solve it. So what does that mean? So we haven't gotten to gadgets yet, but we're talking about ROP. So gadgets, the essence of return-oriented programming is using parts of the assembly against its own program. And so oh no, sorry, I forgot how to find them, but they're here. So gadgets are these little bits of the bytes, the raw bytes in the assembly, and I'm really hoping that SAR approves of my definition this time. They're bits of the or slices of the assembly that, when taken by themselves, look just like assembly operations, and specifically look like assembly operations that end in a return. And so with these return operations, we're able to fully control that. Like, we make little baby functions out of these return gadgets, allowing us to have some control over the registers and what the code is doing. And so there are lots of ways to look for these gadgets. Cutter has a built-in way to search for them, actually, which is kind of cool. If you just do search and then take over here, search in, search for ROP gadgets. We'll do current map sections, and we just do a search for anything. It will find all of our gadgets. Many of them are ridiculous. If I want to just search for return gadgets, I can search that way. Right? There's a leave ret right here, which is easy enough. And in addition to this way of doing it, Pwn Tools has us covered as well. If we do ROP equals ROP on the ELF itself, we can ask for ROP.gadgets. And that also gives us a bunch. And in fact, there may be more here than what is picked up by Cutter. So I found one at 401016, which it looks like this one didn't. But if we do all mapped sections, yeah, that doesn't do any better. Yeah, so for whatever reason, the Pwn Tools one found one that's actually way easier. So this ret is much better. So we'll say ret equals P64. And then we'll do payload plus equals ret to add that gadget at the end. And what we're doing is we're basically spacing out the payload to align it to the size, the size of the stack that the operating system and the CPU is expecting. So sometimes you got to do that. And I'm pretty sure that... Have I already found a field to generate a buffer overflow? Yes, we already have. So what we found is, in general, they're using ISOC 99 scan. So we're good here. You have to add the ret in front of the call to admins only. Right. Okay. Right now, are you trying to gain control of the EIP? No. First of all, we're in 64-bit, so we're not talking about EI anything. We're talking about R. But no, we're doing return-oriented programming. So basically, we're using return codes to send this thing. There's a hidden function in this program called admins only. And so what we're doing is we're overflowing the base pointer over to the return address to get to this admins only. Oh, dang it. There we go. There we go. There we go. Nice. Plants from Outer Space, thank you so much for the follow. That was a fun one. I think I have one more in me for tonight. All right, let's see what number 4 is all about. We will finish this one. We will finish this room. By the way, so next week is going to be a little weird for me because I have to do some traveling. And so I am thinking about, so we'll do Tuesday, but then the week after that, I'm going to be off. So Wednesday and Saturday, I'm going to be off next week. And then I was thinking for the week after, we kind of just have a kind of a summer vacation week. Just have a little fun on stream. Maybe we'll do that Myst playthrough. Open to some other ideas as well. But we don't always have to be serious on this stream. Let's see what this 104 is all about. I am waiting for you at... Oh, interesting. So what is that, whatever that is? We're going to have to learn what that is in... I think Cutter's going to be the right call here. Yeah, so they're giving us a leaked address in memory. And so what are we supposed to do with it? Let's go to main and find out. So it says, I think I have some superpowers, especially executable powers. I'm waiting for you at, and then, so there's this buffer. And the way that this works is that I'm waiting for you at P, and then it calls printf. So it's doing a format string, and I believe if we look at this string, it's at %p. So yeah. It's actually, it's %p, right? And if we do, yeah, it's an address. It's the next address back. So basically it's telling us what the address of the buffer is. Which is interesting because that part sections. Thank you. Whoa. There we go. Segments. Can I put segments up in here? Yeah. Are there any mitigations enabled? Let's find out. Not so far for any of these. Somehow even less, and has read-write executable segments. That's cool. I like that a lot. Look at the sections with the color coding. That's really cool. This is a nice way of doing it. Now, obviously, we're over in stack space, right? But I believe what they're telling us is that the stack is executable. And so, I think we're in shellcode injection territory here, where what we want to do is overflow the buffer, fill it with junk, get it to return to the address, because if they're giving us the address at the start of the buffer, return to that address, nop sled into our shellcode. Bob's your uncle. There's a lot going on there, but I think that's the basic idea. Now, this one is going to be best done, interestingly, because of the nature of it, inside of Pwn tools rather than inside of Rizin. But let's just make sure we understand exactly what's going on here. So, can we go for a fight? Call puts. So it prints out the pointer, and the only pointer it has access to is this buffer. So that's kind of what's going on there. Because those %p's pull from the stack, right? So that's what's there. That's what it pulls. That's what it shows you. And then, so it's printing out that value. And then I'm waiting for you at, right. And then it has, so the buffer is, by the way, how large? If there isn't a win function, if there's no win function, by checking the PLT, got section says reference to system. There, I don't think I saw system anywhere. Look at this. There's no system in the imports. I think this is pretty straight ahead. Yeah. No. And this, by the way, is how I would do that check. Rather than reading the PLT and global offset table manually, the imports here is really handy for exactly that purpose. But right, so they're not giving us much on this one, which is fine. Right, and then it calls read. So this is interesting. Note that the buffer size is 50 or 0x50, right? So the defined buffer size is 80 bytes. Yeah? Okay. But read is kind of interesting. Let's go check the man pages for read as well, right? Oh, not the... Dang it. That's what I wanted. I wanted read 2. Thanks, Wally. Yeah. So the file descriptor, right? The buffer that it's going to read into, and then the size. And note that the size for read, but this is, by the way, supposed to be your safety. But in this case, it's calling read into file descriptor 0, right? That's standard in. That's what we would expect, is reading from standard input. It's reading to the buffer, which, as we said, was 0x50. But then how much is it reading in? It's reading in 200. So it's giving us, in fact, 200 bytes to work with. They're being very cool about that rather than the 50 here, or the 0x50. This is a what we would call a mistaken use of read, right? You're overflowing yourself in that particular case, but nevertheless, we're going to take advantage of it. So what are we going to do with this? It tells us where the stack is, right? And it tells us that we have yeah, that's tricky, because if we have yeah, because just reading it, it's going to blow away the return address, no problem. Yeah. So keep in mind, if we're overflowing to the return address, our actual overflow length, let's try to keep it in there. Overflow len equals 88. And remember, why is it 88? It's because it's 80 to get through the buffer, but then to hit the return address, it's 88. Right? That's the basic idea. So now we need some shellcode. Shellcode is going to be basically sets of assembly instructions encoded in bytes that we're going to give to the program to execute. And that's basically what it's telling us, is that the stack in this particular case is executable. It's marked as executable. So if we can point the program to code that we've put in the stack, then it will run it. This is real bad. You don't want to do this, basically. I mean, there are reasons to do it, but it is a vector for vulnerabilities, as we'll see. Or a vector for exploitation, I should say. Okay. So to prove that we've gotten this right, we're going to do payload equals a times overflow len, and then payload plus equals, let's just do 4Bs. It doesn't actually matter. We just need to beat that return. And then write that in. Okay. And then in Rizin, we're going to fire that up. And we're just going to run it. Okay. So notice that we got an address. It got like moved to the stack, which is kind of interesting. But notice that this address, look at what it has on it. It's got this 42, 42, 42. So we are absolutely hitting it. The reason why it wasn't filled entirely is because we didn't give it enough Bs, basically. We only give it 4 Bs rather than 8. So we give it 4 more Bs. This should fail, actually, at this point, because this address, remember when I said that the 64-bit was going to look for something inside the address space, right? Well, this kind of passed that test, which is why we saw it. And so I'm going to quit that out and try it again. And right, so see, now this time it was like, I'm not running that. What are you doing? If we look at the base pointer, though, you'll see it's all A's. And if we look at the stack pointer, right, there's a bunch of A's, and then right after that, there's a bunch of B's. So we were able to successfully overflow this. Now, here's the trick, though. We don't want to overflow it with A's. We want to overflow it with useful stuff. And that useful stuff is going to be that shellcode that I mentioned, and then some filler. Hey, Beast4. Good to see you. Yeah, dude, we're not always doing Rust. In fact, on Tuesdays we do offensive security stuff. So tonight we're doing binary exploitation. So we're cracking open programs, we're looking at them in assembly, and we're writing shellcode. Well, we're not writing shellcode, we're using shellcode right now. So we're gonna do this, and if I have this right, the first time I try this, I'm gonna get no XCC necessary. I am gonna get an error. But one of the cool things in Pwn Tools is this module called Shellcraft. So Shellcraft has a whole bunch of stuff inside of it. And if we do like shellcraft.amd64.linux, it has these built-in shellcodes. You don't have to use these. There's other places to get cool shellcode from. But one of them that's built in is an SH shellcode. And you can see here, this is the like bytes of, it's actually just a raw string, of the assembly that would make that up. Now, interestingly, I can run ASM on this, theoretically, to turn it into useful bytecode. Except something went wrong. And what went wrong is that it is trying to do it, and you can kind of see it carefully. It's trying to do it for 32 bits by default. I can change that up by setting context.architecture to AMD64. And now when I run the same command, it gives me back a byte string that is that shellcode encoded correctly. Okay. And so pretty cool, right? So we'll call that shellcode. We'll assign that to the variable shellcode. For starters. Other places you can get shellcode. I like Shellstorm. Not secure. Good job, Shellstorm. But it has a lot of great options. If you go to look, Linux x86-64, they've got all sorts of stuff. There's execute bin sh in 27 bytes right here. And they even have the character codes for you if you want them. How long is this len shellcode? 48. So this one's much shorter. So if I needed to get this done in less space, this would be an option. I think I'm going to be okay, though, because our buffer, our overflow length rate is... We have 80 bytes, basically, to work with. Well, 88 bytes, basically, to work with. And so that's fine. And so we're going to do our payload equals... Instead of A's this time, though, what we're going to do... Because remember, we're filling out this buffer with our shellcode, which we want to execute, but we also need to fill up the rest of it with something that's inoffensive, something that the computer will take and kind of just slide through to our code and not worry about. And so that's what's known as a NOP sled. And a NOP is a no-op. Well, you can see them fairly frequently. See if, yeah, there's one right there. There's a no-op. And if we look at that in the hex dump for main, where was I? 4124F. F. There it is. Okay, there's another NOP. So the hex encoding of the NOP instruction is 90. So what we're going to do is we're going to put in a bunch of /x90s. And this is known as a NOP sled. And we're going to times payload, or no, overflow len minus len of the shellcode. Level 5 is you can only use 6 bytes for shellcode. And then from there, payload plus equals shellcode. Len payload is 88, so we got that correct. Okay. Ever seen boot sector FPS? I don't even know what you mean by FPS in that particular context. So no, I certainly have not. But it's cool that you know what it is. Oh, I forgot a thing. Oh, first-person shooter on just the boot sector. Okay, well, I know what FPS means in that context. I've seen the essentially opposite of that. I've seen Doom run on CPU, yeah, this here is a video of Doom getting run on a CPU cluster, which is sort of the exact opposite of what you're talking about. Okay, so the trick is that we're not going to write the payload, right? Because we did, but we're actually not going to use it that way. Here's the reason why. So we're going to do elf equals .104. Okay. And then p equals elf.process. Okay. We're going to do p.receive. Now, this is the kind of thing that you should, get comfortable writing a scripted solution for, but I'm just doing this interactively because, I don't know, it's easy. Wasn't there someone who made Doom run on a pregnancy test? Was that fake? I think that was real. Because there was like an ESP like chip in there. Okay, so here's our address, by the way. So actually our payload is too much. No. Payload's good. Because we've put our payload all in the buffer, right? And then we just do payload plus equals P64, that address. Does the address change each time you run it? Yes, it does. And so you have to use there's a receive until, which you'd like receive until at and then pull the rest using some string parsing. Hey, Real. Just talking about it to tell you how much I like the web app course you developed for the TCM platform. I'm so glad. Thank you so much for saying so, and I'm glad it helped you. Really appreciate that, and I'm glad it was helpful for you. All right, so we've added this address because that's what we want to return to, right? So we'll do p.send payload. Do I have to add a new line? Whoa, Real. Thank you so much for the gift subs. Digital Warhead, Ruza, Owen Coates, Please Fold, and Perryman. Incredibly generous. Really appreciate you giving back. That's super cool of you. That's super cool of you. Oh, or use send line. That's smarter. Let's do that. Okay, and then we'll do p.interactive and see how things look. Ah, got end of file while sending in interactive. Something went awry here. We got a seg fault as well. $88 plus 8 is 96. That should be good. I mean, I'll dollars to donuts. That shellcode was garbage, basically. The built-in shellcode burns me all the time. This one actually does okay for me. So we'll give that a shot. Payload equals. And payload plus equals shellcode. And we'll do p equals. We'll fire it up again. P.receive. Okay. Payload plus equals P64. Pack that address. P.send line. Payload. P.interactive. That didn't work. We got the ls because we were back in interactive Python. That's not working out for me. And it is a different address every time, so that's going to be a little bit tricky. Attach a debugger and see where it's crashing. This is the part that actually sucks using Rizin. Yeah. Let's see. So what's the length of our payload right now? Are we overflowing something? 96. No. Oh, so here's what we can do at least. We can at least send the data. Here, we can do this. With open. The address is going to be wrong. Oh, but we can fix it. Technically. Forget you proper ways to do it. There's no rules. What we can do with Rizin is we can analyze it this way, and we're also gonna set it up in yeah, this is good. So we're gonna analyze it. Seek main, df. I'm waiting for you. Print right here. Actually, we're gonna put a break right here. So there is a Rizin. There is kind of what there is. M alpha is a library to allow you to execute commands from Python into Rizin, but it doesn't have quite the same capabilities as the GDB stuff. To be fair, like, it doesn't have the deep integration that pwtools has with GDB, and this is just me being awful at GDB. But what we can do, there are other ways to solve this problem. So we're gonna run this and hit this breakpoint. So now theoretically this thing has been read. Now, what do we have here? No, we look at like the Rizin Python. Yeah, there's RZ pipe. Here we go. Let's go to the Rizin book. No, those are Python plugins for it. That's not actually what we wanted. We want RZ pipe. Here's how it works. And if I haven't installed this, I will. Sudo pip3 install RZ pipe. Uh-oh. That's annoying. Awesome. There's a rust. But notice what it's doing, right? So you open this thing and then you send these are the Rizin commands, right? So like you can technically do it. It's just a little bit wonkier because you're running the commands and you run DC and then like rz.send, right, or whatever. So yes, you can do it, but I want to try this way. It's going to be a little bit strange. So we've read in the data, right, but it's wrong right now, and I want to fix it. here's what we're gonna do. There's our NOP sled, right? And the first thing I want to do is find so we should see something like A8D0. We should see something like that somewhere. And indeed we do, right? A8D0. So I'm going to take this older address and I'm going to put a breakpoint on there just to see if we hit it. Oh, it's not. Oh, well, we're going to run it and see if we hit it anyway. Okay, so we actually do. Notice we hit DC and we actually hit the address. Right? So we're actually getting to it. But now we have an error. Because, of course, that's not where it actually is. So we're gonna quit this, and we're gonna try this again. And we're gonna put a breakpoint at that same execution point, right? And we're gonna look at the registers. Okay. And, oh, I might have had to open this in write mode. My plan was to basically dynamically edit the stack. But we can do that kind of. So if we go to 80, right? 8D0, 7F. This looks like this is our address right here, right? 7F, FE. So 1, 2, 3, 4, 5, 6, 7, 8. So we want to go to A8D0. 2, 4, 2, 4, 6, 8. So actually we want to go to here. So I'm going to go to, we're going to seek to 9.8. And we have the write capabilities. Write hexadecimal. Perfect. So we're going to write hexadecimal, and what we're going to write, yeah, stack should always be writable. So what we're going to write is, okay, we got this. And so we're going to come over here. I'm going to just P64 it so we have it in the right order easily. Hey, Theo, thank you for the follow. So we're going to write X here. So 40, 55, 65, 34, 83. FF 7F. And I might need to get rid of those spaces. Yo, 5055654583 FF7F. That looks good. So okay, so we broke that a little bit, but kind of on the right track. I'm a little mystified though still as to why, like, plainly we were hitting it the first time. So the question is, let's get that debug going again. And then let's go look at our stack. Okay. So the stack has what we'd expect it to have. The base pointer is at 850. And then where's our D0? Because that's still our payload. There's a bunch of extra stuff here. You found a way of getting Rizin to attach to running Pwn Tool section, but it's a bit of a hack. Yeah? Well, so isn't all of this? No, you don't need to do it with Pwn Tools. You would, but no, because you can set this is just me forgetting how to do something really simple. So Rizin set standard in. No. Yeah, so the trick here is that we have to be able to write unprintable stuff. That's the only problem we're running into here. Start program Pwn Tools, then attach the PID, continue process, and payload from Pwn Tools so I can see a crash. Send the payload from Pwn Tools so I can see a crash in GDB Rizin. Is that not what we're doing? But no. The issue here is that we're executing, like we're hitting the right return address, but there's this extra crap in here. Oh, I'm being stupid. That's our shellcode. I was like, what's all this that isn't 90s? That's the shellcode. Good job, Taggart. Yeah, so that's the shellcode, which is supposed to be there. Yeah. 3B0F05. Yeah, that's our shellcode right there. And then there's our address. So again, I feel like it's just the shellcode that's not working. Let's do a D step Okay, so we hit here. Well, we just did, kind of. Okay, so we're at 8-0. Okay. And all I see is garbage. Oh, sorry. All I see is garbage. Can we play around with the length of the knob sled? Yeah, we can. You think it's too short? I mean, we're hitting the right return address though. Just as a sanity check, because I feel like we've got this, and it might be something on my system that's put the shellcode at the beginning of the buffer, get rid of the knob sled altogether. Yeah, all right. I'll be damned. That worked. So for whatever reason, yeah, putting the knob sled first was messing with it, but putting the payload first worked just fine. Okay, cool. Okay, so con equals 9004. Payload equals... Oh, dang it. Oh no, did we lose the machine? Say expired. Yeah, it does. All right, fine. Fine, you jerk. We'll do this one quickly. Well, I mean, we're pretty much there. Now, I do want to point out that my dumb rewriting the stack method would have in fact worked if we had done the payload first without the shellcode. That would have worked to rewrite the leaked address if we needed to, which is kind of a kludgy way of doing it, but you can do it that way. And actually doing it that way, you could run it through RZ pipe, right? Because you can run seek plus that address and then write whatever you need to into the hex. You could actually have Rizin do the rewriting of the stack for you in Python. That's not a bad idea. All right. Equals, what are we doing? Okay, 9004. Okay, and then on to receive. Okay, we've got the thing. So payload plus equals p64. That con dot send line payload con dot interactive cat flag dot txt. Oh yeah. Nice. All right. That's a cool note to end on. Longer stream than I was expecting to do 4 binary exploitation challenges, but that is how that goes. But okay. That's going to do it for tonight, friends. Thank you so much for hanging out. Always a blast. Spending Tuesdays with y'all. So, I'll be back tomorrow doing some programming. I have no idea what we're going to do, but it'll be code related, code adjacent. And then Saturday, we've got some blue team, as always. And got some cool stuff going for the home lab. I'm pretty excited. And so, if you're still in a stream kind of mood, we're going to pull somebody from the hack list. If you didn't know, there are lots of InfoSec streamers. So, we're going to go check one of them out right now, which is Black Sheep Spicy, who was around earlier and is now streaming. So, drop by on Black Sheep Spicy if you're so inclined. Until next time, though, friends, be good to yourselves, be good to each other, and happy hacking. We'll see ya.